I hope everybody is fine. Uh, and In this video, I'll be discussing quantum spin, and I'll talk about spinors, and then we will lead our discussion to Pauli spin matrices. And to start with spin, we generally understand in classical world, in Newtonian world, spin is actually the motion of a body on account of its axis. So you have a body, and this body can rotate along its axis. And this rotation along the axis of the rotation refers to the spin in classical world. And this is what is the classical, this is how we treat spin in classical mechanics. This is how we treat this spin in Newtonian mechanics. Now, the very first question that arises here is that what is quantum spin? And to answer this question, uh, I should rather say that this spin is basically it is an intrinsic form of angular momentum. So spin is intrinsic. It is intrinsic form of angular momentum. That's basically possessed by the quantum particles, and we have the quantum particles. Which are quantum particles? The quantum particles are they are electrons, they are protons, they are neutrons, uh, and even and even the composite particles like atoms. These atoms, they are also quantum particles. Now, unlike, as I said, in classical mechanics, the angular momentum, if we talk about the angular momentum, this angular momentum arises from the motion of the particle in space. Uh, I mean, or orbital angular momentum. If you have a particle and this particle has a motion in an orbit, this gives rise to the orbital angular momentum. And talking about the spin is basically it's an inherent property of the particles, and it does not depend on the motion. It can be thought. It can be thought like. Uh, it can be thought of as an internal degree of freedom that's associated with a quantum particle. Now, if we lay down a situation like where we have the total angular momentum, generally total angular momentum, and this total angular momentum is J vector. This total angular momentum of a quantum system is basically the sum of orbital angular momentum and spin angular momentum. And it has more generalization in atomic physics. So J is the total angular momentum, and it's the vector sum of the orbital angular momentum and spin angular momentum. Now the point is that this spin angular momentum, again, I would like to tell that this spin angular momentum is the intrinsic property of the particle. Uh, it's not like that it does not have a classical analog. It's an intrinsic property of the particle. It does not describe the motion of a particle as in case of the classical spin. So in quantum mechanics, angular momentum, uh, as we have we have already seen that this angular momentum is quantized. What does that mean? That means it can only take some specific discrete set of values, and the same discreteness, the same discrete values we have for the spin angular momentum associated with the particle in the quantum world. Now, if we talk about this spin quantum number, spin quantum number, in this case, each particle, the particles that I described, like electrons, neutrons, protons, atoms, now each particle has an associated spin quantum number, uh, S, and and this S can take the values, like it can have a value 0, it can have a value 1 by 2, it can have one value, it can have a value of 3 by 2, and so on and so forth. And the total spin angular momentum, as has been done in solving the hydrogen atom problem, the total angular momentum of of a particle. Now, if I say the spin angular momentum, that will be S is under root of S times S plus 1 h bar, where this small s is the spin quantum number, and this s is a representative of spin angular momentum, and h bar is the reduced Planck's constant. Now, if we have electrons, now for electrons, for electrons, not only electrons, for electrons, protons, and neutrons, this S is half. And for photons, photons are also quantum particles. For photons, this spin S is equal to 1. Okay, so this is how we can classify the spin of the fermions, like electrons, neutrons, and protons, with the bosons like photons. So now, if we think in terms of the projection of this spin angular momentum on any axis, now if we want to think, if we want to project this spin angular momentum, the projection of this spin angular momentum, the projection of spin angular momentum, okay, on any axis, and generally what we do, we generally choose that projection as z-axis. We have this angular momentum along the z-axis is quantized as well. Spin angular momentum is as well quantized as we have orbital angular momentum, which is quantized, and we can define that sz as ms h bar, and ms can have the values from minus s to plus s. Now, so this is the concept of spin in its easiest formalism, in its easiest way. Now, talking about spinors, and this spinors is beautifully presented by Landau Lipschitz, which is popularly known as Landau lipstick. It's not lipstick, but for the sake of love, for the sake of favor, it's generally pronounced as Landau lipstick. So this Landau Lipschitz has an extensive explanation of these spinors. Now, to describe, now what are these spinors? In order to describe the spin state of a quantum particle, we use these spinors. And these spinors are special kinds of vectors. They are special kinds of vectors for the the spin-half particles, for spin-half particles. And the state of the particle that's represented here, using this notation, the state of the particle is represented by two component spinors. Two component spinors. And if we have a state vector psi, it can be shown as psi plus and psi minus. Now, what does this? I would like to use a different notation for this as I proceed in analyzing spin, in analyzing these spinors. Now, this psi plus, what it does, it corresponds to the amplitude of finding the particle in spin up state. Spin up state. Now, I will not use psi plus notation. I will use a notation like, I'll use the state vector as spin up. So this refers to spin up state, as psi plus refers to spin up state. I will choose an arrow in the upward direction with a cat as the spin up state, and this psi negative is it's the same thing. It corresponds to the amplitude of finding. It's about finding. It's about finding the particle in the spin-up state, and psi minus is about finding the amplitude of the particle in spin down state. And for spin down, I'll think something like this: arrow pointing down. So this is my spin. This is my spin down. So this psi plus is giving us the measure of the probability of probability of the amplitude of finding the particle in the spin-up state, and psi negative refers to the probability of finding the amplitude of the particle in spin down state. Now, these two components that I've talked about, they form a two-dimensional complex vector space. They don't form a usual three-dimensional vector space as we have in terms of I, j, and k if we talk about Cartesian coordinates. Here, they form a two-dimensional complex vector space, which is totally different. Which is different from the usual three-dimensional vector that are used for the position. That are used for the determination of the position of the particle. The spinor is a mathematical object, so it's not something that can be described in some physical sense, that you have a ball, you threw this ball and it has a trajectory. It's not like that. It's abstract. It's pure mathematical object that transforms in a specific way under rotations. Now, before moving on, I would like to go with some small algebraic ket-bra notation for these for the spin up and spin down. Now, what we have is if I have to think of spin up, this is represented by a column vector 1 0. If I go with the spin down, this is represented by a column vector 0 and 1. So this is the state of spin. This is the state of the spin up. This is the state of the spin down. Now this is ket, and this is also ket. Now I can think of the bra of this spin as it will be 1 and 0 as a row vector, and the bra of spin down will be 0 and 1. Now, since we are talking about the two-dimensional complex state, here we don't have real coordinates, we have complex coordinates. we have complex coordinates. Now, if I think of spin in terms of components, thinking of spin in terms of components. Now, if I think of spin up along x as the ket, and this can be written as 1 by root 2, 1 by root 2, and obviously its bra will be 1 by root 2, 1 by root 2. It will be a row vector. And the spin down along x, this is spin down along x, this is represented as 1 by root 2 minus 1 by root 2. And if I write down its bra, that is spin x, that is 1 by root 2 minus 1 by root 2. This is a row vector. Now, let me do some algebraic mathematics in this context, and these are the notations for this spin along x. Now, if I write something like this, say spin up x, and I take its inner product with spin up of x minus spin down of x and spin down of x. Now I can think of using the matrices that I have. For spin up along x, I have 1 by root 2, then I have again 1 by root 2. Now for this bra, I have 1 by root 2, 1 by root 2, then I have minus spin down, so I have 1 by root 2, 1 by root 2. This is a column vector. Then we have 1 by root 2 minus 1 by root 2. All right, now we would like to solve it. So we have the product of two-dimensional matrices. Okay, so we know how to multiply these matrices, and I want to obtain the resultant matrix of the thing that I have written over here, and it looks so awkward, but let's go with it. So what we have, so I will have 1 by root 2, 1 by root 2 will give me 1 by root 2 whole square, and then I will have another 1 by root 2 whole square, then I will have 1 by root 2 whole square, then I'll have 1 by root 2 whole square. So this will be the first matrix. Then I have minus, then I will have 1 by root 2 whole square, then I will have minus 1 by root 2 whole square, then I will have 1 by root 2 whole square, then I will have minus 1 by root 2 whole square. All right, so I have done nothing. I have just made simple matrix multiplication between the ket of spin up along x and the bra of spin up along x. Then I have to subtract it with the spin down along x in the same case. So this times this is the first term, this times this is the second term, then this times this is the third term, and this times this is the fourth term. So proceeding, so what will I get? I'll get 1 by 2, 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 then minus, I'll get 1 by 2, this is minus 1 by 2, this is 1 by 2, and this is minus 1 by 2. Now I have to subtract the two matrices. So here, this minus this will give me 0, this minus this will give me 1, because minus minus is plus, so 1 by 2 plus 1 by 2 will give me 1. So this plus this will give me 1, and this minus times minus will okay, so this is 1 by 2 minus 1 by 2. Okay, so this is 1 by 2 minus 1 by 2, this will give me 0, that's fine. Then 1 by 2 minus 1 by 2, am I doing it right here? No, I'm not doing it right. I mean, here it is minus, but here it is plus. Okay, this is 1 by root, no, this has to be minus here. Okay, Okay, so no, this is 1 by root 2 minus, yeah, then, you know, yeah, that's it. So this is 1 by root 2 whole square. This is uh, minus 1 by root 2 whole square. This is minus, so minus will come here. So this is minus and this is plus. Okay, so this is minus and this is plus. So we can subtract these two. So this will give me 1 by 2 minus minus is plus. So this will give me 1 and this will give me 0. So what we have 0, 1, 1 and 0. This is called sigma x. So sigma x is nothing but the component of Pauli spin matrices. So this is my sigma x. So this is the measure of Pauli spin matrix along x. Now on similar analysis, we can calculate sigma y, and for that I have to go with the y component of the spin. So for that what I'll do is I have spin up along y times spin up along y minus spin down along y and spin down along y. Okay, so what is this spin up along y? This is 1 by under root 2 I by under root 2. Okay, times spin up along y, the bra, it is automatically 1 by root 2 minus I by root 2 minus this is 1 by root 2 and 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 minus I by root 2. Spin down along y and then spin down along y. It will be the row vector. It will be the row matrix. It will be 1 by root 2. And it's complex conjugate, so it has to be I by root 2. Okay, because this is bra and this is the ket. So so when you write the bra of the ket, you have to change the order of the matrix and you have to take its complex conjugate. So here what I'll have 1 by root 2 whole square. Then here I'll have minus I by root 2 square. So here I will have I by root 2 square. Then I will have minus I square by root 2 square. So this is the product of these two matrices minus. Then here what I'll have 1 by root 2 square. Then we'll have I by root 2 square. Then we'll have minus I by root 2. Then you'll have minus I square by root 2 square. Okay, that should be the case. So what we'll get 1 by 2. Okay, square and root will cancel. Minus I by 2, that's fine. Then here I'll get I by 2 again. Okay, what's wrong here? Why I'm getting, so this is 1 by root 2 and this is, okay, this is I times this. Okay, so here I'm getting minus iota square. We know that iota square is minus 1, so minus minus will be plus, so this will be 1 by 2. Then minus, this will be 1 by 2, this will be I by 2, this will be minus I, it has to be square, minus I by 2, and iota square will be minus 1, minus minus will be plus, so this is 1 by 2. Now we can easily see, so 1 by 2 minus 1 by 2 will give me 0. So I'll get 0. Okay, and minus I by 2 will give me 1 by 2 plus 1 by 2 is 1, so this is minus I. So here I'll get minus I. And then I by 2 and minus I by 2, this is minus minus will give us plus, so this is I. So here I have I, and then I have 1 by 2 minus 1 by 2, that will give us 0. This is nothing but sigma y. So this is our Pauli matrix, the component of Pauli matrix along y-axis, and you can do the similar analysis for for spin up along Z, spin up along Z minus spin down along Z times spin down along Z, and this will result in this will give us a matrix like 1 1 and 0 0. Okay, so this will be over sigma z. So to generalize it now, now for the spin half particles, the Pauli matrices that we have sigma x, we have sigma y, and we have sigma z. They are used to represent these spin operators. They represent these spin operators of whose order is 2 by 2. So we have the matrices of 2 by 2 in all the cases. And they play a crucial role in describing the spin dynamics. So if I think of spin operators like, if I think in terms of, if I try to generalize it like for spin operators, if I think of Sx cap and I think of Sy cap and I think of Sz cap, they are defined in terms of Pauli matrices, and I can generalize that as Si equal to h bar by 2 then sigma I, and this I refers to x, y, and z. All right, and obviously we will have sigma x as we have evaluated it using those vectors as 0 1 1 0, and then sigma y as 0 minus I and 0. So so with this we have concluded the introduction of these spinors, or what we call as spin, and the operators that are associated with the spin of these particles. And after this, I think in the next video we will go with some examples of the experiments that have been performed to demonstrate the spin of these particles. So we'll do that in the next video.